Hello, everyone. Welcome to pre-lecture 19. This is going to be the start of chapter 15 for us, talking about another new form of equilibria. This is solubility equilibria. Okay, so getting going with that. I hope you recall from General Chemistry 1 that the solubility of a substance is going to vary from essentially 0, so being insoluble or sparingly soluble, to something being infinitely soluble. We would call this something totally miscible, right? So you could consider, for example, silver chloride that is going to be sparingly soluble in water. And so if we were to write an equilibrium expression for silver chloride, we could say we start with silver chloride solid and we end up with Ag plus and Cl minus as it partially dissolves in water. If we think about that on the chemical level, say we throw in a chunk of silver chloride into water. As it partially dissolves, some of the silver and chloride will ionize, while some of it is going to remain dissolved. So we reach all the way back to our first unit. We would call this solution being saturated, right? So we are now going to address that saturated solution from the standpoint of equilibrium. And so this is a type of equilibrium called solubility product equilibrium. And so we use the term KSP for this. And so if we were to write the equilibrium expression for our silver chloride, it would be, as always, our products over our reactants. So we'd have silver plus and chloride minus, but in this case, silver chloride, the solid, is our reactant, and it's our only reactant. And because it is a solid, we would not include it in our equilibrium expression. And so that would be our KSP expression. Right? Say we have two of these, a little bit of practice time. And so in both of these solids, they will dissociate the hydroxide part of the molecule. So I'm going to go into these, but I would recommend you pause the video and try and go through them yourself. And so in this first one, we have magnesium hydroxide rather, MgOH2. So with our KSP, our reactant is always going to be a solid, and then it is going to dissolve into solution. So we would end up ionizing to magnesium 2+, which will be aqueous, and then 2 OH-, right, which will also be aqueous. So just a reminder that anytime we have 2 in our subscript of a reactant and something dissolves, we end up with 2 as a coefficient in front of it on our products side. Okay, that would be the first one. I would recommend taking a stab at the second one, this calcium phosphate hydroxide. So if you want to pause the video and do that before I go into it, I'd recommend it. But I'm going to go into it now. So again, we start by writing out calcium phosphate hydroxide, and that is going to be a solid. This is going to be in equilibrium. We dissociate our hydroxide when we ionize. We end up with Ca, I forgot the 5 there, Ca5, PO4, 3, and then this would be minus. That would be dissolved, plus OH minus, which would also be, right? And so this reaction right here, this calcium phosphate hydroxide, is actually the mineral that makes up our teeth. And so if you talk to your dentist about your enamel potentially dissolving, this is the reaction that is going on. This calcium phosphate hydroxide can dissociate, and that is what would weaken our tooth enamel. And so these are the reactions for both of these. If we were to write K expressions for them then, our KSP expression for the top reaction would be our products over our reactants. But because our reactant is a solid, we'd end up with Mg2+ times OH minus. Then we would square that OH minus, right? Because we have a coefficient of 2. So just a reminder, that we do need to remember our coefficients. If we have 2 in front of it, we need to then square it in our equilibrium expression. For our second KSP expression, it would be equal to, again, products of reactants, so CH5, PO43 minus times, oh, and I'm sorry, that wouldn't be minus, that would be plus. I apologize if that confused you. OH minus would be our other half, and then our reactant is a solid, right? So we don't need to do that. Okay, those are our equilibrium expressions for these two reactions. Okay, I'm going to keep moving. And so the KSP for slightly soluble ionic compounds related to its measured solubility. And so essentially, anytime we are measuring a KSP, we have a saturated solution, and we are looking to find out how soluble something is. And so in a lot of these problems, I will ask you what the molar solubility of a particular salt is. What I'm really asking you for is solve for the concentration of the ions, right? So with this, the KSP value can be determined from the equilibrium concentration in molarity, or depending on what you're given, you can also go the other way. So if you're given the molar concentrations at equilibrium, you can solve for KSP, right? Okay, so here's another practice problem. I would recommend, again, giving it a try yourself before I go through it, just so you know how you would approach it, in case it's different from how I approach it. So in this one, the KSP of calcium hydroxide, and I forgot to change that. That shouldn't say calcium, that should say magnesium. So magnesium hydroxide, sorry about that. Magnesium hydroxide is 5.6 times 10 to the negative 12th. Calculate the molar solubility, again, of magnesium hydroxide. So if we were to do this, I would recommend writing your chemical reaction first. And so this was one that we actually just wrote out, right? So MgOH2 is a solid that is in equilibrium with Mg2 plus that is dissolved, and 2OH minus that is also dissolved in aqueous solution. Okay. And we wrote out KSP expression there, which we said is equal to our concentration of Mg2 plus times our concentration of OH minus squared. Right? That squared, again, comes from our coefficient there. So much like our other equilibrium problems, we can solve this by making an ice chart. And so since MgOH2 is a solid, we don't need to include that. We would say that we start with an initial concentration of 0 for both of our products. From there, we would do plus x, and this might be tricky here, but a reminder that this should be plus 2x, because again, our coefficient. So our equilibrium values will be x and 2x for our Mg2 plus and OH minus. So we can plug these equilibrium values into our KSP expression. That means that our KSP is equal to x times 2x squared. And so if we distribute that in, or rather do our exponent and combine terms, we should end up with 4x cubed, right? So the 4 comes from squaring the 2 here to get 4, and then we'd end up with x squared. And so combine all that together, you get 4x cubed. And so we plug in our KSP value, which is given to us in the problem here, 5.6 times 10 to the minus 12, being equal to 4x cubed. Then we solve for x by dividing by each side by 4, and then taking the cubed root. I got a value of x equal to 1.12 times 10 to the minus 4. Okay, that will be equal to our concentration of Mg2 plus, be equal to half the concentration of OH minus. So that would be concentration of OH minus would be double this. So it would be 2.24 times 10 to the negative 4. The reason we would double it is because, again, at equilibrium, we know that our concentration of hydroxide will be equal to 2x. Okay, so that is how you would solve that. Right, I'm going to clear those, and with that, I will bid you farewell for the day. I hope you have a KS special day wherever you are. See you in class.